Right now, at this very moment, the ground beneath your feet is moving, not just spinning through space with our planet, but actually drifting across the Earth's surface at about the same rate your fingernails grow. It's been happening for hundreds of millions of years, and it's still happening now, quietly reshaping our world while you sleep, while you work, while you live your life completely unaware. Welcome to Sleep About Science. Tonight, wherever you are in the world, we're traveling back to witness one of the most extraordinary breakups in Earth's history, the day Pangaea broke apart. And if you drift off to sleep while listening, that's perfectly wonderful. Your dreams might just carry you back to that ancient world. Before we begin, please make yourself comfortable. Pull up your covers, adjust your pillows, maybe dim the lights a little, and remember, this is educational content, not medical advice. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into science. There's something deeply comforting about falling asleep to the vast stories of our planet. Now close your eyes if you'd like, and imagine this. 250 million years ago, if you could have stood anywhere on Earth and looked around, you would have seen something that would make no sense to our modern eyes. There would have been no Atlantic Ocean, no Mediterranean Sea, no English Channel, no gap between Africa and South America, no space between India and Antarctica. Every piece of land we know today was pressed together into one massive supercontinent that geologists call Pangaea, literally meaning all Earth. Picture the most massive jigsaw puzzle you can imagine, where every piece fits together perfectly, but this puzzle is made of continents, and it's about to come apart in the most spectacular geological event our planet has ever known. The story of how Pangaea broke apart isn't just about moving rocks and shifting seas. It's about the very forces that shaped the world where you're lying right now, listening to these words. Let's start with what Pangaea actually looked like, because it's stranger than you might expect. If you could have taken a photograph from space, and I know that's impossible, but bear with me, Pangaea would have looked like a massive, crooked C shape stretching from the North Pole almost to the South Pole. The outside edge of this sea faced what geologists call Panthalassa, meaning all sea, mice, a vast ocean that covered the rest of the planet like a blue blanket. The inside of the sea was filled with a smaller ocean called Tethys, which sounds like a mythological name because it is. Tethys was the Greek tightness of the sea, and this ancient ocean bore her name as it carved a massive gulf into the heart of Pangaea. Think of it like a giant bite taken out of the supercontinent, filled with warm tropical waters that would have lapped against shores that no longer exist. But here's what's truly remarkable about Pangaea. It wasn't stable. Continental crusts, you see, are like puzzle pieces floating on a sea of slowly moving molten rock. And just as puzzle pieces can shift and separate if you shake the table gently enough, the continents of Pangaea were destined to drift apart. The question wasn't if they would separate, but when and how. The answer came about 200 million years ago, during what geologists call the late Triassic period. This is when our story truly begins, not with a bang, but with a whisper. Deep beneath Pangaea's surface, something extraordinary was stirring. Convection currents in the Earth's mantle, those slow, patient rivers of molten rock, began to change their pattern. Think of it like the heating element in your stove, but instead of heating soup, it was heating the entire bottom of a continent. These currents created what scientists call a mantle plume, essentially a massive column of hot rock rising from deep within the earth. Imagine a lava lamp, but instead of pretty colored wax floating in oil, you have continent sized pieces of crust floating on an ocean of molten rock that's been heated from below. When that heat builds up enough, something has to give. And something did give. Around 200 million years ago, Pangaea began to stretch. Not quickly, mind you. Geological time moves at its own pace. But if you could have watched from space across millions of years, you would have seen the supercontinent slowly bulging upward in certain places, like bread dough rising in a warm kitchen. These bulges formed what geologists call rifts, massive cracks in the Earth's surface, where the continental crust was literally being pulled apart. The first major rift system formed right down the middle of Pangaea, running roughly north-south through what would eventually become the Atlantic Ocean. But back then, it wasn't an ocean at all. It was a series of massive valleys, some of them hundreds of miles wide and several miles deep. Picture the Grand Canyon, but imagine it stretching for thousands of miles and being even deeper. These rift valleys were like enormous wounds in the Earth's surface, and into these wounds, something magical began to flow: water. At first, it might have been just streams and rivers, carrying rainwater and snowmelt down into these vast new basins. But as the rifting continued and the valleys grew deeper and wider, something more significant happened. The ocean began to find its way in. The first seawater to flow into these rift valleys came from the Tethys Ocean, that great sea that had been nestled in the heart of Pangaea, like water cupped in your hands. As the rifts deepened and spread, fingers of seawater began to creep inland, creating long, narrow seas that looked remarkably similar to the Red Sea today. But this was just the beginning. As millions of years passed, these narrow seas grew wider. The continental crust on either side of the rifts continued to move apart, driven by that relentless heat from below. And here's where the story gets really fascinating. As the crust pulled apart, new crust began to form in the gaps. Think about pulling apart a piece of warm taffy. As you stretch it, the material in the middle gets thinner and thinner until finally it breaks. But unlike taffy, when continental crust breaks apart, the Earth doesn't just leave an empty space. Instead, molten rock from the mantle below rises up to fill the gap, cooling and hardening into new oceanic crust. This process is happening right now, today, in places like the Mid-Atlantic Ridge, and massive underwater mountain range that runs right down the middle of the Atlantic Ocean. Every year, new rock forms along this ridge, pushing the Americas a little further away from Europe and Africa. It's so slow that you can't feel it, but it's relentless. 200 million years ago, the same process was just getting started in the rifts that would become the Atlantic. Molten rock was rising from the mantle, cooling in the seawater, and forming the very first bits of oceanic crust between the separating pieces of Pangaea. Now you might wonder, why didn't Pangaea break apart all at once? Why was it such a gradual process? The answer lies in the nature of continental crust itself. Unlike the relatively thin oceanic crust that forms at mid-ocean ridges, continental crust is thick and stubborn. It's like trying to tear apart a thick book versus a single sheet of paper. The book, the continental crust, resists breaking, but once it starts to tear, the tear tends to continue along lines of weakness. Pangaea had several such lines of weakness, places where the crust was slightly thinner or had been stressed by previous geological events. The rifting followed these weak spots like water, following the easiest path downhill. This is why the breakup of Pangaea didn't happen uniformly. Some parts separated quickly, while others held together for millions of years longer. The first major break occurred along what would eventually become the Central Atlantic, separating what we now call North America from what would become Europe and Africa. But even this wasn't a clean break. The separation began in the south and slowly propagated northward over millions of years, like a zipper opening from bottom to top. As this separation progressed, something beautiful began to happen in those narrow seas between the continents. Life, which had been constrained to the coastal areas of Pangaea and the Tethys Ocean, suddenly had vast new habitats to explore. Fish swam in waters that had never existed before. Marine reptiles, massive creatures like plesiosaurs and ichthyosaurs, found new hunting grounds in these fresh seaways. The separation wasn't just creating new oceans, it was creating new climates. When all the continents had been joined together in Pangaea, the interior of the supercontinent had been incredibly dry and hot. Imagine the most extreme desert you've ever experienced, then multiply that by 10. With no nearby oceans to moderate the temperature, the inner regions of Pangaea experienced scorching summers and freezing winters. But as the Atlantic began to open, something wonderful happened. Ocean water, with its remarkable ability to store and release heat slowly, began to moderate the climate of the separating continents. Coastal areas that had been brutally hot and dry began to experience more moderate temperatures and increased rainfall. New ecosystems flourished in these changing conditions. The breakup of Pangaea wasn't just one event, though it happened in phases, like a complex dance choreographed by geological forces over hundreds of millions of years. The first phase, which began around 200 million years ago, separated what would become North America and Europe from the southern continents. But the southern part of Pangaea is supercontinent. Within the supercontinent, called Gondwana, remained largely intact for millions of years longer. Gondwana included what we now know as South America, Africa, India, Antarctica, and Australia. For a long time after the northern continents had begun their journey apart, these southern landmasses remained joined together like old friends reluctant to say goodbye. The second major phase of breakup began around 180 million years ago during the Jurassic period. Yes, the same Jurassic you're thinking of, when dinosaurs ruled the Earth. This is when Gondwana itself began to fracture. The first crack appeared between what would become Africa and South America, creating what would eventually grow into the South Atlantic Ocean. But here's something that might surprise you. The southern separation happened differently than the northern one. While the North Atlantic opened relatively quickly in geological terms, the South Atlantic opened like a zipper, starting from the south and slowly working its way north over millions of years. If you could have watched this process in fast forward, you would have seen South America and Africa slowly pivoting away from each other like doors opening on hinges. As these continents separated, something remarkable was happening to the life forms living on them. Families of plants and animals that had once been able to walk or swim from one part of Gondwana to another suddenly found themselves separated by growing oceans. This is why today we find similar fossils and rock formations on opposite sides of the Atlantic Debt. They're like family photographs from before the Great Separation. The evidence for this continental drift is actually quite beautiful when you know how to look for it. In South America and Africa, there are mountain ranges that line up perfectly across the Atlantic, like the two halves of a broken chain. There are coal deposits of the same age and type on both continents, formed in the same ancient swamps before the land was pulled apart. There are glacial deposits that only make sense if these continents were once joined and positioned differently relative to the poles. But perhaps the most compelling evidence comes from the fossils themselves. There's a small reptile called Mesosaurus that lived in freshwater lakes and rivers around 250 million years ago. Mesosaurus fossils are found in both South America and Africa, but nowhere else in the world. This little creature couldn't have swum across an ocean this. It was strictly a freshwater animal. The only way its fossils could be on both continents is if those continents were once connected. The third phase of Pangaea's breakup began around 130 million years ago, and this is when things got really interesting. India, which had been nestled between Africa, Antarctica, and Australia, began its own incredible journey. Like a massive ship setting sail across the ocean, India broke away from the other Gondwanan continents and began racing northward across the Tethys Ocean. And when I say racing, remember that we're talking about geological time. India was moving at about 6 inches per year, fast enough to notice if you lived for millions of years, but certainly not something you could observe in a human lifetime. Still, for a continent, this was remarkably speedy travel. India's journey across the Tethys Ocean is one of the most dramatic stories in geological history. This wasn't just a continent drifting aimlessly, it was a continent with a destination. India was heading straight for Asia, and when these two massive land masses eventually collided around 50 million years ago, the impact would create the Himalayas, the highest mountains on Earth. But let's not get ahead of ourselves. During India's great journey, other parts of Pangaea were still separating too. Australia began pulling away from Antarctica around 100 million years ago, creating the Southern Ocean between them. This separation was gentler than some of the others, more like two dance partners slowly stepping apart than a sudden break. The separation of Australia and Antarctica had profound effects on global climate. When these continents were joined, they acted like a massive dam across the Southern Ocean, preventing the free circulation of water around Antarctica. But once they separated enough to allow ocean currents to flow freely around Antarctica, something remarkable happened. Antarctica became isolated in a ring of cold ocean current, leading to the formation of the massive ice sheets we see today. Meanwhile, the Atlantic Ocean continued to grow wider. By 100 million years ago, it had become a significant body of water, though still much narrower than it is today. Early whales swam in these waters, along with massive marine reptiles that had adapted to life in the expanding ocean. The seabed was actively spreading, creating new oceanic crust along the mid-Atlantic ridge, pushing the continents further and further apart. But Pangaea's breakup wasn't just about the Atlantic. Around the same time, the Pacific Ocean was undergoing its own dramatic changes. The Pacific, which had existed in some form even when Pangaea was intact, began to shrink as the Atlantic grew. It's like a cosmic balance. As new oceanic crust formed in the Atlantic, old oceanic crust in the Pacific was being recycled back into the Earth's mantle through a process called subduction. Picture this process like a massive conveyor belt. New oceanic crust forms at mid-ocean ridges, spreads outward like a slow-moving escalator, and eventually gets pushed back down into the mantle at the edges of the Pacific. This recycling process is still happening today, which is why the Pacific is ringed with volcanoes and earthquakes, which where old ocean floor goes to die and be reborn as new rock. The final major phase of Pangaea's breakup began around 65 million years ago, right around the time the dinosaurs went extinct, though that timing is largely coincidental. This is when the North Atlantic finally completed its opening, fully separating North America from Europe. It's also when some of the most dramatic mountain building episodes in Earth's history occurred. When India finally collided with Asia, the impact was so tremendous that it created not just the Himalayas, but also the Tibetan Plateau, often called the roof of the world. The collision was so powerful that it actually pushed the crust upward to heights that seemed to defy gravity. Mount Everest, that ultimate symbol of Earth's power to create towering peaks, is actually made of limestone that formed on the ocean floor, evidence that even the highest places on our planet were once beneath the sea. But here's something that might help you drift off to sleep with a smile. This incredible story of continental drift and oceanic expansion isn't just ancient history, it's still happening right now as you listen to these words. The Atlantic Ocean is still growing wider by about an inch and a half each year. Europe and North America are still moving away from each other. Africa is slowly rotating counterclockwise and will eventually close the Mediterranean Sea entirely. Australia is sliding northward towards Southeast Asia. In about 50 million years, Maya blink of an eye in geological time, the world map will look completely different again. The Atlantic will be even wider. Africa will have collided with Europe, creating new mountain ranges. Australia might be much closer to Indonesia. The Mediterranean will likely be gone, replaced by a new mountain range as Africa pushes into Europe. And in about 250 million years from now, scientists believe the continents might even come together again to form a new supercontinent. The cycle that began with Pangaea's breakup might complete itself, creating what some researchers playfully call Pangaea Ultima, the last Pangaea, though, of course, it wouldn't really be the last. Earth's continents have been coming together and breaking apart in cycles for billions of years, and they'll likely continue doing so for billions more. This brings us to one of the most beautiful aspects of Pangaea's story. The evidence is all around us, waiting to be noticed. Every time you look at a world map, you're seeing the results of that ancient breakup. The way the eastern coast of South America fits so perfectly with the western coast of Africa isn't a coincidence. They're like two pieces of a puzzle that were once joined together. The Appalachian Mountains in eastern North America line up perfectly with mountain ranges in Scotland and Scandinavia, because they're all part of the same ancient mountain chain that was split apart when the Atlantic Ocean formed. The plants and animals of Madagascar are more similar to those of India than to those of nearby Africa, because Madagascar and India were once neighbors before India began its remarkable journey north. Even the rocks beneath your feet, wherever you are right now, tell the story of Pangaea's breakup. If you live on the eastern coast of North America or the western coast of Europe or Africa, you're living on the edge of continents that were slowly pulled apart by forces so vast and patient that they make human timescales seem like fleeting moments. The process that broke up Pangaea is still shaping our world in ways both subtle and dramatic. The Mid Atlantic Ridge, that underwater mountain range where new oceanic crust is constantly being born, occasionally breaks the surface to create islands like Iceland. Iceland is literally a piece of the mid ocean ridge that has grown tall enough to poke above the waves, and it's still growing, still spreading, still pushing Europe and North America a little further apart each year. The earthquakes that occasionally shake California are related to the same fundamental forces that broke up Pangaea, the Pacific plate, grinding against the North American plate along the San Andreas Fault. The beautiful volcanic islands of Hawaii, formed as the Pacific plate, moved slowly over a hot spot in the mantle, creating a chain of islands like bread coming out of an oven one loaf at a time. But perhaps the most remarkable thing about Pangaea's breakup is how it demonstrates the incredible patience of geological forces. The entire process, from the first rifting to the formation of the modern Atlantic Ocean, took nearly 200 million years. That's roughly 1,000 times longer than modern humans have existed. It's a timescale so vast that our minds can barely grasp it. Yet, in another sense, it's happening quickly. 200 million years sounds like forever, but in the context of Earth's 4.5 billion year history, it's just the most recent chapter. Earth has seen supercontinents form and break apart multiple times before Pangaea, and it will see them form and break apart again long after our current continental arrangement becomes ancient history. Scientists believe there was a supercontinent called Rodinia that existed around 1 billion years ago, long before complex life had evolved on Earth. Rodinia broke apart, and the pieces eventually came back together to form Pangaea. Before Rodinia, there might have been other supercontinents whose names we'll never know, whose stories are lost in the deep time before complex life existed to leave fossils. The cyclical nature of continental drift formation, breakup, and reformation is driven by the same fundamental process that powers our planet from within. Deep in the Earth's core, radioactive elements are constantly decaying, releasing heat that has been driving geological processes for billions of years. This heat creates the convection currents in the mantle that move the continents around like leaves floating on a slowly stirring pond. It's a process so slow and steady that it's easy to think of our planet as static and unchanging. But the story of Pangaea reminds us that Earth is incredibly dynamic. The ground beneath us is in constant, if imperceptible, motion. The very atoms in the rock under your house might have once been part of a mountain range on the other side of the world, or part of a coral reef in a tropical sea that no longer exists. Think about this as you drift toward sleep. Every grain of sand, every pebble, every massive boulder has a story that spans hundreds of millions of years. The calcium in your bones might have once been part of a coral reef in the Tethys Ocean. The iron in your blood might have been forged in the heart of a star that died before Pangaea even existed, then incorporated into the earth and eventually into the continental crust that would be pulled apart to form the Atlantic. We are quite literally made of the same materials that witnessed Pangaea's great breakup. The atoms in your body have been on an extraordinary journey through space and time, and right now they're arranged in such a way that they can contemplate their own history. You are the universe becoming aware of itself, lying here in the dark, learning about the forces that shaped the very ground beneath you. As you settle deeper into sleep, let your mind wander back to that ancient world of Pangaea. Picture vast deserts where the interior of the supercontinent baked under relentless sun. Imagine the first cracks appearing in the earth, so small at first that you could step across them, but destined to become the mighty Atlantic Ocean. Think about the first drops of seawater trickling into those early rifts, not knowing they were beginning to fill what would become one of Earth's major oceans. Picture the dinosaurs that lived through this transition, completely unaware that the ground beneath their feet was slowly, patiently preparing to separate into different continents. Consider the plants and animals that found themselves on opposite sides of new oceans as Pangaea broke apart, suddenly isolated from their relatives, beginning the long process of evolving into new species adapted to their new homes. The baobab trees of Madagascar and Australia share a common ancestor that lived when these landmasses were connected. The similar but distinct marsupials of South America and Australia tell the story of Gondwana's ancient unity and eventual separation. There's something deeply soothing about geological time, isn't there? In a world where everything seems to happen so quickly, where changes occur from moment to moment and year to year, there's comfort in knowing that some changes happen on timescales that make our worries seem small and temporary. The mountains that seem so permanent will eventually be worn down by wind and rain. The oceans that seem so vast and unchanging are constantly shifting and growing. Even the continents, those massive foundations of our world, are in constant motion, dancing slowly across the planet's surface to rhythms we can barely perceive. And yet, for all their slow majesty, these geological processes are also remarkably similar to things we can understand on human scales. The heat that drives continental drift works like the heating in your house. Warmer material rises, cooler material sinks, creating circulation patterns that move everything around. The way continents break apart is like ice cracking on a frozen lake. It follows lines of weakness and creates patterns that seem almost artistic in their complexity. The formation of new oceanic crust is like a healing wound, where the earth repairs the gaps created by continental separation with fresh rock from deep within. The collision of continents is like two pieces of clay being pressed together. They bulge upward at the point of contact, creating mountain ranges that stand as monuments to incredible forces. As the Atlantic Ocean continued to widen over millions of years, life on the separating continents began to diverge in fascinating ways. South America, now isolated from Africa by a growing ocean, became home to unique creatures that evolved nowhere else on Earth. Giant ground sloths roamed its plains. Massive flightless birds, called terror birds, ruled its forests. Armadillo-like creatures, the size of cars, grazed in its grasslands. Meanwhile, across the widening Atlantic, Africa was developing its own distinctive fauna. Early elephants, ancestors of both modern African elephants and the mammoths that would later spread across the northern continents, evolved in Africa's changing landscapes. Early primates swung through forests that were becoming more diverse as Africa's climate became more varied due to its changing position and the growing influence of the Atlantic's moderating waters. The story of Pangaea's breakup is also intimately connected with the story of life itself. When Pangaea was intact, terrestrial life was relatively uniform across the supercontinent. Dinosaurs could walk from one end of the landmass to the other, and indeed, we find very similar dinosaur fossils from the Triassic period in places as far apart as Argentina and Connecticut. But as the continents separated, terrestrial life became increasingly isolated and began to evolve in different directions. This isolation and subsequent evolution is why today we have such incredible biological diversity around the world. The unique animals of Australia, kangaroos, koalas, platypuses, evolved in isolation after Australia separated from the other continents. The distinctive plants of South America developed after that continent broke away from Africa. In a very real sense, Pangaea's breakup created the biological diversity we see on Earth today. Without continental drift, without the isolation that occurs when land masses separate, evolution might have proceeded quite differently. We might live in a world where the same few types of animals and plants existed everywhere, adapted to the relatively uniform conditions of a single supercontinent. Instead, we live in a world where every continent tells a different evolutionary story, where isolation and adaptation have created countless unique forms of life. The Amazon rainforest, the African savanna, the Australian outback. Each of these incredible ecosystems exists partly because continental drift gave evolution the space and time to experiment with new forms of life. The breakup of Pangaea also had profound effects on Earth's oceans and atmosphere. When all the continents were joined together, ocean circulation patterns were quite different from what we see today. The massive Panthalassa Ocean that surrounded Pangaea had its own circulation patterns, and the smaller Tethys Sea that cut into the supercontinent created different currents and climate zones. As the Atlantic Ocean formed and grew wider, it fundamentally changed how water moved around the planet. New currents formed, carrying warm water from the tropics toward the poles and bringing cold water from the poles toward the equator. These currents, which we can see today in patterns like the Gulf Stream, help moderate Earth's climate and distribute heat around the globe. The formation of new ocean basins also changed how carbon moved through Earth's systems. Oceans absorb massive amounts of carbon dioxide from the atmosphere, and as new ocean area was created during Pangaea's breakup, the planet's capacity to absorb atmospheric carbon changed. This had subtle but important effects on global climate over millions of years. The breakup process itself was sometimes dramatic in ways that might seem impossible today. When continents separate, they don't always do so smoothly. Sometimes the crust stretches and thins until it breaks catastrophically, creating what geologists call flood basal provinces, massive outpourings of lava that can cover areas the size of modern countries. One of these events, called the Central Atlantic Magmatic Province, occurred right around the time Pangaea began to break apart. Imagine lava flowing across an area larger than the entire United States, releasing enormous amounts of gas and ash into the atmosphere. This event was so massive that it likely contributed to one of Earth's major extinction events, clearing the way for new forms of life to evolve in the changing world. But even these catastrophic events were part of the patient, long-term process of planetary change. The Earth has a remarkable ability to recover from even the most dramatic geological events, to rebuild and reshape itself over millions of years. The scars left by the breakup of Pangaea became the foundations for new continents, new oceans, and new forms of life. As you lie there listening to this story, consider that you're part of this ongoing process. The carbon atoms in your body might have been released into the atmosphere during one of those ancient volcanic episodes, then absorbed by a plant, then consumed by an animal, then returned to the earth, then eventually incorporated into your own body. You are made of recycled stardust, that has been cycling through Earth's systems for billions of years. The water in your body might once have filled the Tethys Ocean, that ancient sea that no longer exists except in the imagination of geologists. It might have rained on Pangaea's vast deserts, or filled the first narrow seas that formed as the supercontinent began to break apart. Every molecule of water has been on an incredible journey, and right now, some of those molecules are helping to keep you alive as you listen to the story of their ancient travels. There's something profoundly peaceful about imagining yourself as part of this vast, slow dance of continents and oceans. Your problems, your worries, your daily concerns exist on one timescale, while the great forces that shaped our planet operate on another timescale entirely. Neither is more important than the other, but there's comfort in knowing that you're part of something much larger and more enduring than the immediate moment. The rocks in the foundation of your house, the soil in your garden, the mountains visible from your window, they all tell parts of the Pangaea story. Even if you live nowhere near an ocean, the land around you was shaped by the forces that broke up the supercontinent. River valleys carved by water flowing toward the new seas, mountain ranges uplifted by the compression and tension of continental separation, plains formed by the erosion of ancient highlands. It's all connected to that great breakup that began 200 million years ago. And here's something wonderful to think about. As you drift towards sleep, the story isn't over. Right now, tonight, as you rest, the continents are still moving. The Atlantic is still growing wider, grain by grain, inch by inch. The Pacific is still shrinking. New mountains are slowly rising, while old mountains are gradually worn away by rain and wind and time. In your lifetime, the continents will move several feet. It's not enough to notice, but it's enough to be real, enough to be part of the continuing story that began when Pangaea first started to crack apart. You are living through another chapter in the greatest slow motion adventure story ever told, the story of how planets reshape themselves across deep time. Scientists who study continental drift often speak of it with something approaching poetry. They talk about continents dancing across the Earth's surface, about ocean basins breathing as they expand and contract, about mountain ranges growing toward the sky. This isn't just metaphorical language, it reflects a real sense that our planet is alive in ways we're only beginning to understand. The breakup of Pangaea also gives us a humbling perspective on human civilization. Everything we've built, our cities, our roads, our monuments, exists on continental crust that is constantly, if imperceptibly, in motion. The Pyramid of Giza has moved several inches since it was built, not because it's falling down, but because the African continent itself has shifted slightly in its slow journey across the Earth's surface. Rome has moved relative to London. New York has moved relative to Paris. Not by much, maybe a few feet over the centuries, but enough to remind us that even our most permanent seeming achievements are passengers on a planet that never stops changing. Yet there's something beautiful about this constant change. It means that Earth is still alive, still active, still creating new landscapes and new opportunities for life. A static planet might seem more stable, but it would also be a dead planet. The forces that broke up Pangaea are the same forces that continue to renew and reshape our world, ensuring that Earth remains a dynamic, living planet. As we near the end of our journey back to Pangaea's breakup, Let's take a moment to appreciate the incredible detective work that allowed scientists to piece together this story. When Alfred Wegener first proposed the idea of continental drift in the early 1900s, he was ridiculed by much of the scientific community. The idea that continents could move seemed absurd. They were so massive, so seemingly permanent. But Wegener persisted, collecting evidence from around the world. He noticed that similar fossils existed on continents, now separated by vast oceans. He observed that mountain ranges seemed to line up across ocean basins. He documented the way coastlines fit together like puzzle pieces. Slowly, quietly, patiently, he built the case for a mobile Earth. It wasn't until the 1960s that scientists discovered the mechanism that makes continental drift possible: plate tectonics. The theory of plate tectonics revealed that Earth's surface is broken into massive plates that float on the partially molten mantle below. These plates move slowly but constantly, driven by heat from the planet's interior. When plates move apart, new oceanic crust forms between them. When plates move together, one might slide beneath the other, or they might collide and create mountain ranges. When plates slide past each other, they create the kinds of faults that cause earthquakes. All of these processes can be traced back to the same fundamental driver mill as the heat engine inside our planet that has been running for billions of years. The discovery of plate tectonics was like suddenly understanding the grammar of a language you'd been hearing all your life. Suddenly, earthquakes, volcanoes, mountain ranges, and ocean basins all made sense as parts of a single unified system. The breakup of Pangaea wasn't a mysterious one-time event. It was just one episode in the ongoing story of plate tectonics. Today, scientists can measure continental drift directly using GPS satellites. They can track the movement of continents to within millimeters, watching in real time as the Atlantic widens and the Pacific narrows. They can predict where earthquakes are likely to occur by understanding how plates interact. They can even model what the Earth might look like millions of years in the future. But for all our technological sophistication, there's still something magical about the basic story of Pangaea's breakup. It reminds us that we live on a planet that is far more dynamic and alive than it might appear from our brief human perspective. The solid ground beneath our feet is actually floating on a sea of molten rock, driven by heat from radioactive decay deep in the Earth's core. The mountains that seem so permanent are actually temporary features, pushed up by continental collisions and then slowly worn away by erosion. The oceans that seem so eternal are actually quite young in geological terms. The Atlantic didn't exist for most of Earth's history, and it will eventually be recycled back into the mantle as the continental dance continues. As you settle into sleep tonight, imagine yourself drifting back through time to witness Pangaea's great breakup. Picture standing on the shore of that first narrow sea as it formed between the separating continents. Feel the warm winds blowing across landscapes that no longer exist. Watch the sun set over oceans that were just beginning to be born. Imagine the patience of those early seas, filling slowly over millions of years as the continents crept apart, grain by grain. Think about the first marine creatures to swim in Atlantic waters, exploring brand new ocean territories that had never existed before. Picture the plants and animals that found themselves on opposite sides of widening gaps, beginning the long process of adapting to separation. The story of Pangaea's breakup is ultimately a story about change vast, patient, unstoppable change that operates on timescales that dwarf human experience, but that nevertheless shapes every aspect of the world we inhabit. It's a reminder that permanence is an illusion, that everything we see around us is part of ongoing processes of transformation that began billions of years ago and will continue for billions of years to come. But it's also a story about connection. Despite the vast distances that now separate the continents, despite the oceans that seem to divide our world into separate realms, everything is still connected by this shared history. The rocks of South America remember being joined to Africa. The mountains of Scandinavia remember being connected to those of Appalachia. The entire earth remembers being Pangaea, even as it continues its slow transformation into whatever comes next. There's a beautiful recursion in this story. Just as Pangaea formed from the collision of earlier, smaller continents, the breakup of Pangaea is leading toward the formation of future supercontinents. The cycle continues, driven by the same patient forces that have been reshaping our planet for billions of years. In about 250 million years, when our distant descendants, if they exist, look back at our current world, they might see our familiar continents the way we now see Pangaea, as an ancient arrangement that seems almost unimaginable, a curious phase in Earth's long history of continental reorganization. The Atlantic Ocean, which seems so permanent and vast to us, will be just a memory preserved in the geological record. The Mediterranean Sea will have closed as Africa continues its slow collision with Europe. New mountain ranges will have risen, and ancient ones will have been worn away to nothing. But the process itself, the patient, unstoppable dance of continents across the Earth's surface, will continue. Deep in the planet's interior, radioactive elements will still be decaying, still generating the heat that drives the great convection currents in the mantle. Plates will still move, continents will still drift, oceans will still open and close. This continuity is perhaps the most remarkable aspect of Pangaea's story. It connects us not just to the deep past, but to the deep future. We are living through one moment in an epic story that began when the earth first formed and will continue until the sun eventually expands and makes our planet uninhabitable billions of years from now. But that's far too distant to worry about tonight. Tonight, it's enough to rest in the knowledge that we live on a dynamic, living planet that is constantly creating new wonders, even as it transforms old ones into something entirely different. The breakup of Pangaea was just one chapter in this endless story of transformation, but what a chapter it was. From a single supercontinent surrounded by a single ocean, Earth created the diverse, beautiful world we see today. The seven continents, separated by five oceans, each with its own character, its own climate, its own unique collection of life forms. The Amazon rainforest, the Sahara Desert, the Himalayas, the Great Barrier Reef. None of these would exist without the breakup of Pangaea. And so, as you drift off to sleep, know that you're resting on a planet that never stops creating beauty through patient transformation. The same forces that broke up Pangaea are still at work tonight, still shaping tomorrow's landscapes, still writing the next chapters in Earth's magnificent story. Sweet dreams, fellow travelers through space and time. May your sleep be filled with the quiet wonder of geological deep time, where mountains rise like slow growing flowers and continents drift like leaves on a cosmic pond. The earth continues its ancient dance beneath you, and you are part of that dance, made of the same materials, shaped by the same forces, connected to the same incredible story that began when Pangaea first started to crack apart and will continue long after we're gone. Sleep well, wherever you are in this beautiful dynamic world that Pangaea's breakup helped create. Tomorrow, when you wake, you'll be on a planet that has moved just a tiny bit further in its great continental dance, carrying you along on a journey that spans deep time itself. Good night.